Hi guys, so my name is Yukmo Patel and I'm currently pursuing Masters in Software Engineering here at San State University. And today I'll be presenting a comprehensive overview of Graph Foundation models for recommendation. And so, based on the recent survey paper by Wu, published in 2025, this is an exciting area of research that combines the strengths of graph neural networks and large language models to create more effective recommender systems. Over next 20 to 25 minutes, I'll walk you through the key concepts, approaches, challenges, and future directions in this rapidly evolving field. So, first we'll start with presentation outline. And so, first, let me outline what we'll cover today. So, at first, I'll provide an introduction to recommender systems and their importance in today's data landscape. Then, I will discuss the limitations of current approaches, particularly highlighting the challenges faced by GNN-based and LLM-based recommender systems. Then, next, I'll introduce Graph Foundation models as a paradigm that addresses these limitations by integrating the strengths of both approaches. We'll then dive into a detailed taxonomy um, of GFM-based recommender systems, exploring three main categories. And finally, we'll examine key challenges facing these models and potential future research directions before concluding with a summary of key takeaways. So, now we'll dive into introduction to recommender systems. So, recommender systems have become essential components of digital landscape, powering personalized experiences across numerous platforms and services. These systems help users navigate vast amounts of information by suggesting content, products, or services that align with their preferences and interests. Traditional approaches to recommendation include collaborative filtering, which suggests items based on similar users' preferences, and content based filtering, which focuses on item attributes and user profiles. While these methods have been successful, they face limitations in handling sparse data and capturing complex relationships. So, recent advances have led to deep learning based approaches with graph neural networks and large language models emerging as two dominant paradigms in the field. Uh, GNNs excel at modeling the structural relationships between users and items, while LLMs bring powerful language understanding capabilities to the table. So now we'll move on to our fourth slide, which is the challenge in recommendations. So in that, we have data types, GNN limitations, LLM limitations. So before diving into graph foundation models, it's important to understand the fundamental challenge in recommendation systems today. So the data in recommender systems typically consists of both structural information like user item interactions and textual information such as user profiles and item descriptions. Each of our current approaches excels in handling one type of information but struggles with the other. GNN-based recommender systems are excellent at capturing the structural aspects and modeling higher order relationships in user item interaction graphs. However, they face significant limitations when dealing with textual information, as the sequential order and semantic meaning of words are difficult to represent with graph structures. On the other hand, LLM-based recommender systems, with their robust contextual understanding and word knowledge, excel at processing textual descriptions. However, they struggle with complex relationships between entities due to their sequential modeling design and limited reasoning capabilities for higher order structural information. So this creates a fundamental gap in our ability to fully leverage both types of information for more accurate and personalized. recommendations. So now we'll move on to current approaches comparison. So GNN based RS and LLM based RS. So let's compare the two dominant approaches in more detail to better understand their strengths and limitations. So GNN-based recommender systems excel at capturing higher order relationships between users and items through graph structures. They can model user preferences based on multi-hop neighbors, effectively leveraging the collaborative filtering signals in the data. This enables them to make accurate recommendations based on interaction patterns. However, they cannot effectively handle textual information due to their structural bias. LLM based recommender systems, on the other hand, benefit from their strong contextual understanding and ability to process rich textual descriptions. They can comprehend user reviews, item features, and other textual content to extract meaningful insights. However, they struggle with complex relation structures because their sequential modeling design limits their ability to reason about higher order connections. Each approach excels in one domain but falls short in the other, highlighting the need for an integrated solution that combines their strengths. And now we'll move on to graph foundation models. In that, this is where graph foundation models come in. So GFMs represent a significant paradigm shift in recommendation technology, inspired by the success of language foundation models in NLP. So these models are pre-trained on large datasets that incorporate graph structures to solve graph-related tasks. They integrate GNN and LLM technologies to efficiently utilize both structural and textual data to align user preferences and make more precise recommendations with minimized bias. A key characteristic of GFMs is that they acquire emergence and homogenization during pre-training, enabling them to adapt seamlessly across various downstream tasks. By integrating both graph learning and language understanding, they create a more holistic approach to recommendation that addresses the limitations of previous methods. Then our next topic is taxonomy of GFM based recommenders. So in that, first we have graph augmented LLM, LLM augmented graph, LLM graph harmonization. So based on synergistic relationship between graphs and LLMs in GFMs, we can categorize the related works into three principal categories. First, graph augmented LLM approaches inject structural information from graphs into LLMs to enhance their reasoning and generation capabilities for recommendation. Then, second is LLM augmented graph methods that take the opposite approach, using LLMs to enhance either the structural or textual information in the graph. Third is LLM graph harmonization techniques aim to combine the semantic embeddings in LLMs and structural embeddings in graphs to achieve mutual optimization and maximize recommendation performance. This taxonomy helps us understand how different approaches leverage the complementary strengths of GNNs and LLMs to create more effective recommender systems. Next, we will move on to graph augmented LLMs. In that, we'll discuss about key challenge, approach for approach 1 and approach 2. So let's start by exploring graph augmented LLM approaches in more detail. So LLMs excel at understanding and generating text, but struggle with complex relation structures inherent in recommender systems. The key challenge here is designing effective cross-model interfaces that bridge graph structures to language models. How do we translate structural information from graphs into a format that LLMs can understand and process? So these methods can be categorized into two main approaches. Token level infusion integrates structural information directly at the token level, representing nodes or subgraphs as spatial tokens within the LLM's input. Context level infusion provides structural information as context to the LLM either through the text descriptions or implicit retrieval, avoiding modifications to the LLM's architecture. So each approach offers different trade-offs in terms of integration flexibility and computational requirements. So next one is token level infusion method. In that we have syntax integrated injection and syntax decoupled injections. Yeah, so token level infusion can be implemented in two main ways, which is syntax integrated injection embeds special tokens as syntactic components within the LLM's input sequence. So, for example, TMF introduces tokens like view or purchase to represent user actions with embeddings learned from a multi-behavior graph. LLMGR goes further by modifying the LLM's output layer, allowing it to directly generate item tokens as recommendations. Syntax decoupled injection takes a different approach by appending graph embeddings as prefixes or suffixes, separating structural information from the main textual prompt. Extract prepends GNN learned embeddings representing user item relationships, while Compass combines user queries with knowledge graph embeddings to guide the LLM. These methods differ in how tightly they integrate structural information with the LLM's processing mechanisms. Next is context level infusion methods. So, context level infusion provides structural information to the LLMs as context rather than modifying its token processing. So, explicit graph to text mapping converts graph structures into natural language descriptions that the LLM can process directly. For example, a graph path like user A, purchase, then item B, payment, credit card might be translated to A purchased B with a credit card. Systems like at GCOD like extract multi-hop neighbors from a heterogeneous graph and create natural language descriptions, while KGREC extract, extracts knowledge graph nodes and inserts them into prompt templates. Implicit graph retrieval uses GNN embeddings to retrieve relevant information semantically, and CLAGKG encodes a legal knowledge graph and retrieves relevant provisions based on embedding similarity, while URLLM retrieves historical interactions to provide cross-domain preference information. So this approach leverages the LLM's natural language processing capabilities without requiring modifications to its architecture. Now next is LLM augmented graph. So now let's shift our focus to LLM augmented graph approaches. Rather than modifying the LLM, these methods aim to enhance the graph data using the LLM's capabilities, thereby improving the effectiveness of subsequent GNN-based recommendation. The core idea is to leverage the world knowledge and natural language processing capabilities of LLMs to augment graph data before it's processed by GNNs. These methods can be categorized into two main approaches. Topology augmentation modifies the structure of the graph itself, adding new nodes or edges based on LLM-derived insights. Feature augmentation enhances the features of nodes in the graph without changing its topology using the LLM's natural language processing capabilities. Each approach offers different ways to incorporate the LLM's knowledge into the graph representation. Now, topology augmentation. So, topology augmentation restructures graph data using LLMs to convert textual information into structured format, thereby modifying the topological structure of the graph. Edge level expansion introduces new relationships between nodes in the data. For instance, LLM KERAC employs LLMs to access complementary between pairs of items, establishing new relationships in the graph. So, SAGCN extracts user opinions on items across multiple attributes to construct distinct graphs for each attribute. Node level expansion leverages the world knowledge and contextual reasoning capabilities of LLMs to use auxiliary information as new nodes. Autograph encodes the textual information of users and items, followed by quantizing the semantic embeddings to derive fine-grained auxiliary information. Topic KG generates topic nodes to enhance the graph structure. These methods effectively utilize the LLM's knowledge to influence the training of subsequent GNNs by introducing new structural information. Now, next is future augmentation. So, in this, rather than altering the graph structure, feature augmentation focuses on improving node features without changing the topology. So, this approach leverages the natural language processing capabilities of LLMs to enhance data at the textual or embedding level, thereby influencing subsequent recommendations. For example, GSC LLM integrates the stages of LLM and GNN, with the LLM performing textual message passing and aggregation for each node in the graph. LIKR employs LLMs to analyze user interaction histories to derive user preferred item attributes, which then serve as rewards for reinforcement learning within the graph. P4R enhances the textual information of nodes by constructing appropriate prompts for input into LLMs. These methods show how LLMs can improve node representations without changing the graph structure itself. Now, next is LLM graph harmonization. So, LLM graph harmonization represents a more balanced approach that aims to optimally combine the computational efficiency, adaptability, and reasoning capabilities of both GNNs and LLMs. The key idea is to balance textual and structural embeddings to create a unified representation that leverages the strengths of both modalities. Two main approaches emerge in this category. Embedding fusion directly combines LLM derived textual representations with graph learned structural embeddings to create a unified feature space. Embedding alignment focuses on recording the heterogeneity between embeddings from different modalities by mapping them into shared space to enhance consistency and coherence. So this approach is aimed to create more integrated representations that benefit from both textual understanding and structural awareness. Now, next is embedding fusion. So, embedding fusion combines complementary textual and structural information to create a unified representation space. So, the LLM incorporates graph structures into LLMs through dynamic memory enhanced fusion. It uses a dual flow interaction mechanism where one flow learns from GNN updated dynamic embeddings reflecting user item interaction, while the other adapts LLM generated embeddings based on real time textual content. So LKPNR combines LLMs with knowledge graphs for personalized news recommendation, leveraging the semantic richness of LLMs to generate high quality news presentations while using knowledge graphs to capture the relation structure of news entities. This approach directly exploits the contextual richness of LLMs alongside the relational structures captured by GNNs, enabling efficient utilization of both textual and graph data. Now we'll move on to embedding alignment. So embedding alignment takes a different approach by focusing on reconciling the heterogeneity between embeddings from different modalities. This strategy ensures that embeddings from both modalities can operate coherently within a unified representational space, reducing information loss and noise. DALR aligns structural embeddings from GNNs with semantic embeddings from LLMs through contrastive learning paradigms, mitigating semantic gaps and noise introduced by the inherently different data sources. LLM-REC employs a denoised data robustification mechanism to enhance the reliability of augmented recommendation data, while R RLM-REC leverages contrastive alignment strategies to bridge the semantic space of LLMs within the collaboration signals from GNNs. So these methods excel at unifying heterogeneous modalities, ensuring consistent representation learning that facilitates between downstream recommendation tasks. So next are challenges. So despite their promise, GFM-based recommender systems face several significant challenges. Computational cost and scalability issues arise from the substantial resources required for large-scale deployment. The integration of graph-based reasoning and LLM inference results in high memory consumption and slow inference speed, particularly when processing dense user item graphs or generating real-time recommendations. Robustness against noisy data is another challenge. Real-world user interactions are inherently noisy within with short-term fluctuations, incomplete preferences, and potential adversarial perturbation. GFMs introduce additional sources of noise from both structured and unstructured data, requiring advanced denoising techniques to maintain recommendation accuracy. Now, more challenges. Additional challenges include multimodal information fusion, where diverse data modalities like text, graphs, images, and audio must be integrated effectively despite their varying granularity and semantic gaps. So, the lack of end-to-end optimization presents another hurdle. Current recommendation systems often employ a multi-stage process that requires significant resources to optimize. End-to-end generative approaches that encapsulate multi-stages could reduce complexity but require further research. Finally, the knowledge preference gap represents a fundamental misalignment between globally pre-trained world knowledge and personalized user preferences. LLM-based models may generate factually coherent but overly neutral content, whereas users often respond more favorably to engaging or personalized content. Now, next is future directions. So, looking forward, several promising research directions emerge to address these challenges. Efficient model compression strategies could reduce the computational demands of graph enhanced LLMs, while adaptive graph specification techniques might maintain performance while reducing overhead. So, self-supervised denoising techniques and adversarial training tailored for multimodal representation could improve robustness against noisy and adversarial data. Adaptive fusion frameworks and cross-model alignment mechanisms could enhance multimodal information integration, while end-to-end generative recommendation approaches might simplify the recommendation pipeline. Finally, preference-aware knowledge adaptation methods could help bridge the gap between um, global knowledge and personal preferences, creating more engaging and personalized recommendations. Now, in the conclusion, key takeaways of GFMs or recommendation are integration strengths, main approaches, challenges remain, and future potential. So this presentation is based on comprehensive survey by Wu, titled Graph Foundation Models for Recommendation, a comprehensive survey published on arXiv in 2025. I encourage you to refer to the study for more in-depth analysis of the methods and approaches discussed today. Thank you for your attention throughout this presentation. I welcome any questions or feedback you may have about Graph Foundation models for recommendation systems. Your insights and perspectives would be valuable in furthering our understanding of this exciting field. Thank you.